Yeah, but like summer remember too.
Yeah, because we were ones that went to school together.
I guess.
That makes sense.
She gets mad at me like every day because I call her Pookie. I know, but she hates it. I don't know why. I go visit her at work and I say, hey, Cookie Bear. And she hates it. Yeah. I still have a B. Go me. What? I didn't hear you. There's a Blackboard app.
It sucks.
Okay, then I won't get it.
Well, I feel like I should since I live in the whole
The web browser is better than
Kristen gave me a goodie bag.
that one. That
I got one too.
Oh, it wasn't Kristen.
Let's see, there's college and career Logos hand sanitizer. Stickers. I love stickers.
So let's start by warming up on this problem. So see if we can remember what we were doing on Monday. And we'll probably throw some problems on the board. And so while y'all are working on that, I'll talk about the midterm, at least for a little bit. So I was actually very pleased with the midterm grades. So they came out really well. So normally my average is closer to like a 70, but this year's average was like about a 79. So that's really high. So that's pretty high for a chemistry or a science, any science class average. And so even looking at like the distribution, so there were like a lot of, so there were very few like high A's, but there were a lot of like low A's and high B's, so that was really good. And so there were some lower scores too, but I'm not too concerned at the moment. And so I wanted to put that out there for people. So, right, this is a 100 level course. My goal is not to fail anybody if you're showing up, right, doing all the work, at least attempting the midterms. And the midterm grades, none of them were so low that I feel like I need to offer corrections. So that's where I'm thinking with the corrections. I think that the labs and other assignments will help buffer people out, and I think that will be okay grade-wise. So I'm not worried about anybody grade-wise, so just continue to turn in like all your assignments. Overall, this class I've been pretty pleased with. You seem like you're on top of things, especially compared to my other classes or other years, so great job, y'all. Oh, yeah. And then I assume you still need some time. So look back at your notes, ask your neighbors, how do we start this? Even if you're not sure of what to do, like maybe what key pieces of information should we start with? So what are people thinking right now? What might we need to find? Any thoughts? So we're given just grams of magnesium hydroxide. And then what can we do with this? What are we trying to find? So it asks us mass of HCl in grams. So where do we go from here? What do we need? So what are some thoughts then? You mean HCl?
Yeah, HCl.
Yep, so let's do that. So we'll need this molecular weight eventually. And so let's add that up. So it's like 1. And again, your answer could vary with rounding. So now we have about 36.45 or so grams per mole for our molecular weight. What else could we calculate, or do we need? Excellent, so let's get that. So does, and I don't remember magnesium, I think it's like 24-ish. And oxygen, so 16 times 2, hydrogen. And then somebody give me a more accurate molecular weight than my chicken scratch. What'd you say, 50?
58.3.
So 58.3 grams per mole or something like that. So again, right, you can have a little bit of discrepancy with your rounding here depending on what values you're pulling and how much you're rounding, but something like that. So now what do we do with this information? We can always look back at our mole highway, so we always want to get to moles, right? So that's how we can compare these quantities, just like we did with our s'mores. So how do we go from grams to moles then? I think I heard somebody like whisper it. Yeah. So divide by the molecular weight. So, and right, so this is just dimensional analysis. We can look at our chart to help us. So, okay, we have mass in grams. Now it says divide by molecular weight. So good. And I'll just label this magnesium hydroxide. And then bidimensional analysis. So, of course, we have grams per mole. That's just our formula weight. So now we can see if we divide, that gives us grams on bottom, moles on top. So we're left with moles. And while I pull out my calculator, someone can also let me know what they got. I see some nods. And so we should have 0.0559 moles or so. And so that's moles of magnesium hydroxide. And so now what do we do with this information? What's the next step? what do we do with our moles? Why do we want to be with our moles? Yeah, so mole-mole ratio. So now let's go back to our formula, or our balanced equation. And so we're interested in HCl, so we already got the molecular weight of that. So now we just need to look at their mole-mole ratio. And so we can tell they're in a 1:2 ratio. And so I'm just going to write that as our next step. So we'll take magnesium hydroxide. And so from our equation, we say from every 1 equivalent of magnesium hydroxide, we need 2 of HCl. And so of course you can just multiply it by 2. I'm just setting up everything more formally so we can tell. So 2. So moles of magnesium hydroxide cancels. And so we get about 0.112 moles of our hydrochloric acid. And so now what do we do from there? We're basically there. So we have moles of HCl. We know the molecular weight. It wants mass. So what's the last step? Yep, so now we multiply, and then again, just by dimensional analysis, you see that that makes sense as well. So moles, multiply it by grams per mole. And so your answer may vary slightly with rounding. So I get about 4 grams roughly. So questions on this one? And kind of remembering from Monday. Let's see. So let's look at this practice problem. And so now, looking at this reaction, so this is kind of an unusual way to synthesize ammonia, but you could add nitrous oxide and hydrogen gas, and you would get ammonia and water. And so if you have 86.3 grams of NO and 25.6 grams of hydrogen, what's your theoretical yield of ammonia? So think about the last problem too, what we had to do. How is it the same? How is it different? So while y'all are working, so what are we doing? How do we approach this problem? So, excellent. So it looks like you want to find, so you're just doing kind of the process for NO, finding the yield, and then did you repeat it for H2? All right, excellent. So that was a good approach, right? So we basically have to do what we did before twice. And so looks like Trinity is just going through the steps here. So we need to find moles of NO. And so, right, did everybody get this for the molecular weight? So you just add them. So that all looks good there. So did we get 2.88 moles of NO? And so now what do we do with this quantity? So I like, you said the mole ratio, and then we could wait to calculate the theoretical yield. So what's the molecular weight of NH3? So 17 grams per mole. And so we don't have to do this right at this step, but let's do what she said. So let's take that 2.88 moles and at least compare, right, our mole ratio, so NO to ammonia, except they're 1-to-1, so you could recognize that this is how many moles of product. So I'll just write it out, though. So comparing our mole ratio. So that cancels. Now we get 2.88 moles of ammonia. And so if we want to convert it to grams, then we multiply it by 17. Yeah.
So you would find the molecular weight of NH3 and not H2?
The H2O.
Yeah, because in the problem it says 25.6 grams of H2.
Oh, so we're going to do that in a second. So we're going to have to repeat this whole process. Right? So first what we're doing is basically we're saying, well, how much ammonia can I make with 86.3 grams of NO? And then so we have that answer, at least in moles. So we could stop here. And then, yeah, so now we have to repeat it, though, for H2. So let's go ahead and do that, because we're trying to find which one is our limiting reagent. And so now let's repeat. So 1 mole, so don't forget it's a diatomic, so it should be about 2 grams per mole. And so that gives you about 12.8 moles of H2. But then what's the ratio now? Exactly. So 2 to 5. So make sure you plug in those numbers. Now let's do that. So 12.8 moles of H2. But we said now, so for 5 moles of H2, we get 2 ammonia. So again, just pulling that from our balanced equation. And so now I'll have to use my calculator. So times 3 divided by, times 2 divided by 3. And so I get 8.53 moles of product of ammonia. Oh, did I divide? I divided by the wrong thing, didn't 25.6 divided by 5, sorry. Does 5.12 sound better? Okay. So 5.12 moles of ammonia then. And so now looking at this data, so which one is our limiting reagent? But from, so would it be the NO or the H2? So the NO, excellent, so it made the least. And so now let's label that, oh, that was not a different color. It's a different color. So now we can say that's our limiting reagent. And so now if we want to find the theoretical yield in grams, now let's go ahead and take this 2.88, and now we can multiply it by the molecular weight we found earlier of 17. Now I'll just say, so from our limiting reagent, we had 2.88 moles of ammonia, so times 17 grams per mole. And so then for our final answer, I get like 48 point, I'll just round it to 49 roughly, with sig figs, as I was kind of loose with my numbers. So about 49 grams total? 17. Questions on that problem?
Okay, so we got the 4.8 grams of NH3, but are we still doing the percent yield or?
So they didn't tell us what actual yield in this problem, so we just calculated theoretical. So they would have had to have said like, oh, if we got, 36 grams, what's the percent yield? But they didn't give us any of that information in this problem. All right, let's hit up other reaction types before I forget, and then we'll do more stoichiometry practice, and we'll do kind of harder practice where it's just going to be like words, and you'll have to put it all together. So just as a recap, so we talked about our combustion reaction, so that was just burning. We mentioned our combination combustion type reactions, so you saw some of those in lab with your magnesium and oxygen burning. And so now let's look at our other types of reaction. So we have a single replacement. And can someone give an example from lab? What did that look like? What's some example? You might have to think back. It's a single replacement. Some examples. Anybody? So how can we tell if we have a single replacement? What are some clues? So kind of like a one swapping. So here's kind of the general form. So A plus BC gives us some sort of BAC, right? And then what were some examples of? Can we think of any that we've seen? We saw one in lab, at least. What was that reaction where you had like a metal and then a solution and they like made a new metal? So what about that reaction where you had a piece of zinc metal and you added it to that blue copper sulfate solution? And then remember how they kind of swap places, the metal ions, and so then you started making copper back out, and then the zinc sulfate went back into solution. And so the key things you're looking for is, right, A here should be something in its elemental form. And so usually it's a metal, but I just want to bring up, there could be other examples. So we could take, let's just take iron bromide, for example, plus chlorine gas. So, right, chlorine 2, so even though it looks a little different, still in its elemental form. I'll just put that, right, so it's still elemental. So it's still considered single replacement. And then same thing, we can swap and make bromine gas, so elemental form, and iron chloride. So we don't usually see this in lab, so that'd be like trickier to do this. Obviously, right, chlorine is a gas, so we'd have to generate it and add it. And so this is a lot simpler, so that we see this, of course, in lab and safer. But so that's what you're looking for with single replacement. And so what was double replacement? What happens? What's the general form? Yeah, so they swap partners. That's a good way of phrasing it. And so, like she was saying, they both tend to be ionic compounds, right? So they could be polyatomics or something. But as long as there's cation, anion, and then they swap cation partners, then we get AD, CB. And then, so don't forget the also special case of our double replacement decomposition reaction. And so that usually happens when we make like carbonic acid or something, it will decompose. So we've looked at those scenarios. So just kind of be aware of that. So what was our reaction from lab? It was sodium carbonate, right, plus HCl, so then you do the double displacement, and we made our carbonic acid, which decomposed, and of course our salt. And so this is good, and so I want to talk about something briefly, but then we'll kind of revisit this later, because we really didn't talk about, well, what drives a double replacement reaction? You kind of saw it in lab, but we didn't really clarify. And so the double replacement reaction, it is either driven by two things, so that's a precipitation. So you have to have some sort of solid forming. And so later we'll come back to this and we'll go over some like solubility rules. And if it's not precipitation, it's going to be water formation, such as in like a neutralization reaction. And so just a quick example of a precipitation reaction is, so we can have sodium chloride plus silver nitrate, and then so the partners swap like y'all were telling me, and so that gives us silver chloride. And so silver chloride is insoluble. Again, we don't know that right now, but we'll revisit this topic later. So then this is what's driving it. It drops out of solution, and then our sodium nitrate just hangs out as ion still, which we indicate as AQ. And then let's just give a general neutralization reaction. And again, we'll revisit acids and bases at the very end, but some basic reaction could look like sodium hydroxide plus hydrochloric acid. So again, do the double displacement to give you water plus our salt. And of course, salt stays in solution, and water drives that reaction forward. And so last ones we should mention would just be like a decomposition reaction. And so that would just be anything kind of decomposing. So you could take, let's just do calcium carbonate, and then we can decompose it into calcium oxide plus CO2. So that would be one example of a decomposition reaction. And of course, decomposition, you can tell it's decomposition since you always have more products than you do reactants. So some sort of A goes to BC. So again, more products than reactants. Okay. Let's see how far we can get with this. All right, so let's try this limiting reagent sheet that I shamelessly stole. But I like it because now we kind of have to put everything together. So this is what I'm saying, like chemistry by nature is cumulative. And so let's take just a minute or so to start the first part of this. So write your balanced equation that occurs when iron 2 chloride is mixed with sodium phosphate, forming iron 2 phosphate and sodium chloride. So just take it step by step, right? Write the proper formula for each one of these compounds that it lists, and then use the coefficients to balance. So in the interest of time, I'm just going to start kind of writing this out. And so I'm just doing the sketch work. So iron 2 plus, right, from our Roman numeral. And so then swap trick gives us our formula, so we can at least write this properly. So same thing, sodium phosphate, so phosphate PO4 3 minus, sodium 1 plus, so our swap trick. And so it gives us iron 2 phosphate. And so again, I'm just doing my swap trick. So 3 and 2. So we can write everything properly. And then sodium chloride, so that's NaCl. So this is like step number 1 or 0.5, whatever you want to think of it. And then you just need a balance using our coefficients. Let's see. I'm just trying to balance. Does that look like what people got? Sorry, we're kind of rushing a little. And so now see if we can do this problem. So once we have this, right, so now we're ready. So now I have 23 grams of iron 2 chloride reacts with 41 grams of sodium phosphate. So now we have another limiting reagent question and how much sodium chloride can be formed. Do you have a question? So trying to help people out. So other steps in this, so right, get your molecular weights of iron chloride and sodium phosphate. And so let me know if this looks funny or not. And so now let's do this. And again, I'm kind of somewhat rushing-ish. So we will have our quiz still, and I'll still give you a 10-minute break once we're done. I just wanted to finish. So calculating moles of iron chloride. So I get 0.11, or sorry, 0.1181 moles of iron chloride. But then we need to look at our equation. So if we're looking at sodium chloride, they're in a 3:6 ratio. So times 6 over 3. So you could do times 2 as well. So I'm just going to do it times 2 in my calculator. So 0.36 moles of product. And then repeat for sodium phosphate. So 41 grams. Divide by our molecular weight. So then I get 0.25 moles of sodium phosphate. So then going back to our equation, they're a 2:6 ratio, so times 3. So what's my limiting reagent? So that would be the product though, right? So, but then which one made less, right? Was it the iron chloride or the sodium phosphate? So iron chloride, and so now we just star this one, so this is our limiting reagent. So that's how many moles of NaCl can be formed. And so let's convert it, or at least be prepared to convert it to grams. So this is a good question. So how much of the excess reagent remains when this reaction has gone to completion? So how do we determine that? What do we need to calculate? Yeah, so let's do that. So now we kind of have to go back and do some more math. And so let's now start with this number, right? Okay, well this was my limiting reagent. So 0.181 moles of iron chloride. And so now we need to answer, well, how much sodium phosphate did we actually use? And so let's go to our equation. So they're in a 3:2 ratio. So 3 moles of iron chloride goes on bottom, 2 moles of our sodium phosphate goes on top. Again, just from our equation. So 0.181, and then times this ratio, so 2/3. And so now this is how much we actually use. So we actually need 0.120 moles of our sodium phosphate. And so they didn't tell us whether they wanted it in grams or moles. And so for the sake of brevity, it's in moles here. So let's go ahead and just subtract that. So 0.25 moles, so that's what we had, minus what we actually needed. And so that gives us 0.129 moles remain. And of course we could convert it back to grams if we wanted to, so multiply it by 163. But again, it was ambiguous, so you could have left it like that. I'll just put it as an alternative answer, so 21.2 grams. And so now the last step, so now we need to find our mass. So they gave us now our actual yield, so 16.1 grams of sodium chloride in our hands. So let's go back to this problem. So we said 0.36 moles, and let's see, the mass of sodium chloride is 58.443. Yeah.
So for the math just now with the moles and what's left over, you add them? I thought you said subtract.
Oh, yeah, I did subtract. So I did the 0.125 minus. or sorry, 0.25 minus 0.12. So I subtracted these two, right? So 0.25 minus 0.120. And that's how I got that remain. Does that make sense, or? Well, we could.
It's simple stuff, not.
Well, we can recap because other people might be confused, right? So this is what we said we had, right? So we had this amount total, just starting from this 41 grams. But then we said this was our limiting reagent, so we had to recalculate how much we actually used, right? So this is what was actually consumed, just based off of this iron chloride calculation. So then we did the moles, found that we actually consumed 0.120 moles. Yeah, and then we subtracted that. And then last little bit, so 0.36 times 58.443. And so we have a theoretical yield of 21.04 grams of sodium chloride. So in hand was 16, so now 16 divided by our 21.04 times 100. And so that gives us about a 76.5% yield, or so not too bad of a reaction there. All right, so in the interest of time, we will end there. So we do have a quiz. So it's just going to be kind of basic stuff, like what's a single bond, what's a double bond, some prefixes, some covalent naming, and then a little bit about like structures. And so I don't think it should be too bad. And so take your 10-minute break, and then we'll come back to the quiz. But then afterwards, right, make sure you're asking questions for the stoichiometry help, especially if you're not getting it. So it's just a lot of little steps, right? So you just want to make sure you feel comfortable with the process. All right.